Let's finish up these notes. Logistic growth. So exponential growth usually grows exponentially. Logistic growth means that something grows exponentially to a point and then it kind of tapers off. It's not going to get bigger infinitely because it can only reach a certain value. We call that logistic growth. So write down this definition. In a confined environment, the exponential growth rate may not stay constant. Sometimes a population can only be sustained to a certain point. And then I drew the graph earlier, but let's draw it again. So it looks something like this, where it starts out as an exponential function, but then it tapers off. And we call that a logistic growth model. I am on the last page of my notes. The next concept that goes with this is something called the carrying capacity. The carrying capacity is the maximum sustainable population or the largest population an environment can support. The largest population an environment can support. So if a population grows, like a population of bacteria in a petri dish or something, eventually it's going to fill up the petri dish and it can't grow any further. If you have a population of rabbits in a secluded area or a fenced off area, eventually there's going to be so many rabbits there won't be enough food to sustain them all. So carrying capacity is the maximum sustainable population. It means the highest amount that something can get based on its environmental factors. Okay, so next is the formula for logistic growth. Write this down. P of n, Pn equals Pn minus 1 plus R 1 minus Pn minus 1 over K times Pn minus 1. That's a crazy long formula. K represents the carrying capacity, and R represents the growth rate. So here's an example. A forest has 200 rabbits in any given perimeter of land. Okay, but it's estimated to be able to sustain 2,000 rabbits. Should be able to sustain 2,000 rabbits. Rabbits grow at around 50% population per year. I should say rabbits grow 50% per year. Can you predict a future population? Let's see if we can figure this out. Okay, let's go ahead and just play with the rabbit numbers for a minute. We can make a table based on the year and then the population of rabbits. So year 0 we have 200. At the end of year 1 our rabbits have grown let's back up for a minute before we go to the table, and let's go ahead and figure out our formula. Okay, so we probably should have put a box around that. So Pn is our final amount. So predict a future population. Let's go ahead and figure out P1. Okay, so P1 is P0, and P0 is 200, plus R, and R is 0.5, times 1 minus P and minus 1 again, that's P0, P0, 200 over K, and our K for this problem is 2,000, because that's how much we think the forest can support. And then we multiply that by, again, Pn minus 1, and Pn minus 1 is your P0 again, so times 200. You can pause the movie and calculate that on your own, but you should get 290. So after year 1, we're at 290. So let's try this again. P2, everywhere we saw 200 before, we're going to replace that with 290. So 290 plus 0.5 times 1 minus. This is 290 over 2,000 times 290. And I'll let you go ahead and figure out what that is. So could we predict a population in the future? Yes, we would have to. This is a recursive formula, you'll notice. So we would have to find all of the different numbers as we go along to get a higher up one. Okay. One more thing as you're thinking about this, logistic models, they do sometimes oscillate at the top. So even though they're reaching this carrying capacity, they could go up and down, up and down, up and down when they get to the top. Just know that that happens sometimes to make them more interesting.